Welcome to Chapter 2, where we will explore electrochromic materials and their unique properties. This video will focus on the science and engineering of electrochromic materials, the architecture of light and color. Electrochromic materials reversibly change optical properties when an applied potential drives a redox process, coupled with ion motion. This electrochemistry edits the material's electronic structure, influencing how it interacts with photons. This slide provides an advanced technical explainer. The relationship R plus A plus T equals 1 describes how a surface reflects, absorbs, and transmits light. Applications include saving energy in smart windows and instantly eliminating glare in auto-dimming rearview mirrors. Incident radiation interacts with the material through reflection, direct transmission, absorption, or diffraction and refraction, resulting in transmitted radiation. Color contrast in electrochromic materials can be quantified as the change in absorbance, delta A, or the percentage change in transmittance, delta %T, between the bleached and colored states. A generic electrochromic device comprises 5 superimposed layers on a transparent substrate. Variable optical transmittance results from electrochromic films, changing their optical absorption as ions are inserted or extracted via a centrally positioned electrolyte. Ions move within the device when a small electrical field of about 1 volt DC is applied between 2 transparent electrical conductors, making powering easy, even with photovoltaics. Electrochromic devices have 2 main behaviors. Self-erasing, or type 1/2, requires continuous current to sustain color. Bistable, or type 3, sustains colored or bleached states for hours or days without continuous power, drawing energy only during switching. Transition metal oxides and Prussian blue exhibit bistable behavior. We now explore quasi-particles in the window, specifically how polaron and bipolaron hopping drive dual-band absorption in electrochromic oxides. The polaron concept, proposed by Landau and Pekar, describes an electron moving through a dielectric crystal. It displaces surrounding atoms, screening its charge and effectively dressing itself in a phonon cloud. This self-trapping lowers electron mobility and increases its effective mass. The physics of self-trapping are governed by the Froelich-Hamiltonian. The electron-phonon interaction strength is defined by the dimensionless coupling constant, alpha. Strong interactions in polar materials lead to stable polaron formation. Polarons interact uniquely with light. In intervalence transfer, the energy needed for a polaron to hop between lattice sites creates a distinct optical absorption peak, the Franck-Condon peak. The peak position is approximately 4 times the polaron activation energy. Amorphous cathodic oxides are used in smart windows for their ability to reversibly change color when ions and electrons are injected. While the macroscopic effect is known, the exact origin of optical absorption at the atomic scale remains controversial. A unifying model suggests that coloration in amorphous cathodic electrochromic oxides is universally described by a combination of 2 distinct quantum hopping mechanisms: single polaron hopping for near-infrared modulation, and bipolaron hopping for visible light modulation. Mechanism 1 is single polaron hopping. It has a low activation energy of about 0.2 to 0.3 electron volts. It dominates the near-infrared absorption band and is triggered during the initial stages of electron or lithium-ion insertion, as base metallic valences are reduced by 1. Mechanism 2 is bipolaron hopping. It requires higher photon energy with an activation energy of about 0.55 to 0.75 electron volts. It dominates the visible light absorption region, emerging as more electrons are inserted and Mn2 plus sites form. In amorphous materials, absorption peaks are asymmetric due to density of states effects. The Brixen model assumes a Gaussian density of states, accurately predicting this asymmetry based on the Fermi level's position. In a case study on tungsten oxide, the intercalation of lithium ions exhibits classic dual-band modulation. The early phase involves single polaron hopping, causing a massive drop in near-infrared transmission. The late phase features bipolaron hopping, drastically dropping visible light transmission. The Brixen polaron theory perfectly fits the experimental spectra. X-ray photoelectron spectroscopy, or XPS, verifies the valence shift. The pristine state is dominated by W6+. At 45 minutes, W5+ emerges, activating single polaron hopping in the near-infrared. At 120 minutes, W4+ emerges, consuming W5+ and activating bipolaron hopping in the visible range. This video will explore the mechanics of electrochromic switching in Prussian blue, which is characterized by a mixed valence electron and ion insertion switch. Prussian blue pigment consists of iron cations, cyanide anions, and water. Its formal name is iron 3 hexacyanoferrate 2. The complex contains both Fe2 and Fe3 oxidation states. Electrochromic switching involves the electrochemical toggling of Fe oxidation states. Ion insertion or extraction, such as with K+, maintains electroneutrality. The intense native blue color comes from an intervalence charge transfer transition. This electron hop creates a strong optical absorption band at 700 nanometers, characteristic of the mixed valence framework. Applied potential simultaneously drives solid-state redox reactions and boundary ion motion. Voltage changes the Fe oxidation states, while electrolyte ions move in or out to maintain electroneutrality. Reduction suppresses the Fe2, Fe3 pair, bleaching the film to Prussian white. An electron is inserted, reducing Fe3 to Fe2. The 700 nanometers IVCT band disappears, making the film nearly colorless. Cation insertion, such as K+, is strictly required to compensate for the injected electrons during reduction. This insertion step occurs during the negative redox waves. Oxidation removes an electron and shifts the absorption to a 420 nanometers band, turning the film brown or yellow. The 700 nanometers IVCT band is completely gone. Anion diffusion governs charge compensation during the higher potential oxidation process. Anions must travel through the crystal, and their identity significantly affects kinetic speed and film stability. The open zeolitic framework imposes strict hydrated ion size constraints. Based on size arguments, only K+, Rb+, CS+, and NH4+ transport well through the lattice. Stable long-term cycling in aqueous electrolytes relies exclusively on potassium. Modern measurements confirm K+ is optimal, allowing reversible lattice deformation without fracturing the framework. In summary, Prussian white is Fe2 dominant and colorless, requiring K+ insertion. Prussian blue is mixed Fe2, Fe3, and blue. The fully oxidized state is Fe3, dominant, brown/yellow, and requires anion diffusion. This video explores programming matter using Viologen transfer, which is a visual synthesis of multi-responsive smart materials and crystallographic breakthroughs. The color gradient shows controlled electron transfer, shifting the material through distinct, programmed states. Smart materials alter their optical properties in response to external physical excitations like temperature, light, pressure, and moisture. The next generation of materials relies on highly efficient, solid-state redox processes, transferring electrons without breaking molecular bonds. Viologens are redox-active, electron-deficient molecules. They form brilliantly colored radicals through a one-electron reduction. The photoinduced electron transfer process occurs without bond cleavage, minimizing physical disturbance and enabling highly reversible solid-state chromism. Previously, Viologen photochromic behavior was restricted to anaerobic conditions due to rapid oxidation in the air. By locking Viologen units into a dense metal-organic framework, the crystal packing physically blocks oxygen diffusion, stabilizing the radicals in the air for months. The first stimulus is pressure. A Viologen compound demonstrates that extreme mechanical pressure can force a reversible color change without breaking covalent bonds. The compressed state shows a strong signal confirming the generation of stable radicals. Pressure acts as a brute force structural manipulator, altering the distance between the electron-rich donor and the electron-deficient acceptor. The NO donor-acceptor contacts shrink, forcing the components into the proximity required for electron transfer to occur. Using diamond anvil cell technology, we can track hydrostatic compression. Upon compression, new intense absorption bands emerge, shifting the crystal to a deep red state. As pressure releases, the bands undergo a regular blue shift, landing in the green radical state. The third stimulus is moisture, resulting in the chromic sponge effect. Heating or applying a desiccant induces the same electron transfer and green radical formation as pressure or light. Dehydration collapses the internal architecture, bringing groups close to trigger electron transfer. The anhydrous green phase exhibits radical stability, persisting even when heated to 250 degrees Celsius. This state is instantly reversible. Exposure to water expands the lattice, triggering back electron transfer and recovering the EPR silent yellow state. Molecular stacking architecture dictates the speed of color change. Comparing two vialogen complexes, one synthesized with zinc and the other with cobalt, shows massive disparities. Isolated layers lead to a slow transition, while tightly stacked layers enable a rapid transition. The difference in reaction kinetics is due to component alignment. The zinc compound operates via slow intramolecular electron transfer. The cobalt compound forces face-to-face pi-pi stacking, creating a massive intermolecular electron transfer highway. A unified theory of chromic design reveals that across different stimuli, light, pressure, and dehydration, distance determines function. Future multi-responsive coatings will be programmed by selectively tuning these intermolecular distances. Next-gen innovation includes dual-band electrochromism. This device independently modulates invisible NIR heat and visible light. Faradaic niobium oxide and plasmonic ITO nanoparticles are key components in this structure. An electrochromic device is a highly optimized, large-scale electrochemical cell. Key layers include the substrate, primary electrochromic layer, ionic electrolyte, ion storage layer, and bottom substrate. Quantitative performance metrics for electrochromic devices include optical density, a logarithmic measure of absorption. Another metric is switching time, which measures the duration required to achieve 90% of the total available optical change. Industrial scale-up relies on vacuum deposition, which dominates the commercial smart window sector. This method provides large area optical uniformity and strict nanometer-level thickness control, which wet chemical solutions cannot achieve at massive scales. Electrochromic engineering promises a shift from the quantum level of amorphous oxides to dynamic, energy-saving facades, creating sustainable skylines worldwide.